Hello everyone, welcome back to MindMatrix Learning. So in this video, I'll be continuing with the solutions of the AI problems we had. So we had, I guess, 5 to 6 problems related to the AI. So now I'll be solving two problems, which I've handled, for which I created the question. Okay. So let me just talk about that. By now, you should be having this clear-cut idea about the giveaway announcements, the quality of questions as being asked by many students to increase the number of tests, as they are loving it and they are asking it to make it paid. So I hope you're getting like everything for free. So like it's a good opportunity. Just share it with your friends, and you also enroll into the test series for GATE DA. Okay. So yeah, with respect to the AI, we had this question. There was other part of this question which was very simple. It was just calculating the min and max thing. Over here we needed to calculate like which node would be pruned uh, when we use the alpha beta search. Now before talking about the alpha beta search or the problem solving, let me just give you a little bit of idea how does alpha beta pruning or alpha beta search works. Okay, so to talk about that, I'll just give you the brief intro so that it helps everyone. So default values, let me just talk about that. So by default, the alpha is the lower bound, beta is the upper bound. And if I talk about v value, v is the value of node. Okay, so it generally should be in the range of alpha and beta, which we try to find out. Okay, so by default, when I'm talking about the v value of any node, now there are two types of node we are having, min and max. So when we actually find out, so alpha is the alpha is the lower bound, so we always keep it minus infinity, we keep it infinity. If I talk about the value of v at min node, so I'm always looking at minimum of all the child. So right now by default we consider the value to be infinity, so that if I get any other child which is having lower value, I'll just use that value. For an example, 3 and infinity, which one is minimum? 3. So you'll use 3 there. Okay. Similarly, for a max node, by default, the value you take is minus infinity, so that when for the max node you are considering the max value, you'll consider the max of the node value and the child. So in that case, you'll get a better value always. Okay. So these are the default values which you pick up. Now, how does alpha beta pruning or alpha beta search works? Let me give you the context around that also. So there are two things. When you are at min node, what is happening in that case? When you are at max node, what is happening in that case? So I'll just give you that clarification, so that if somebody doesn't know or have a doubt in like how does this work, they just get it properly. Okay, and don't forget to like and share it with your friends. Okay, or comment down if you really like this video or like the explanation. For a min node, what we do is basically we keep on calculating the value of the node, v value, basically the value of the node, with the help of the already default value we have by default, or we keep on updating with the help of child. So for an example, if this is the node, so I'll just look for, okay, this is the value, this is the value, this is the value. We'll figure out, okay, whatever is minimum, and we'll try to assign it. So over here, while watching it out, I can do it faster, but as a part of algorithm we do it one by one. What is minimum of this and this, will update it, this and this will update it, this and this update it. That's how we update the minimum value of the node. Okay, so that's how it happens. So we always just look for v is equal to the value of min node. It would always be min of what, the v and the child value, whatever we had. Okay, so right now, whatever is the value I'm having, and then whatever is the child value, we'll try to update it. Now the thing is, see, alpha, this v value, we always want it to be in the range of alpha and beta. Always remember, we always try to ensure this. If this is the case, it's good. If not, either pruning takes place or no update takes place. So once we get this, we'll try to check at this place that, okay, whether v I have got is greater than alpha or not. Okay, so I want in between alpha and beta. If it is between alpha and beta, then it's good. If not, then there is a problem. So if v is less than equal to alpha, in that case what we do is we simply return v value. We simply return, we do not do any kind of an update, we don't see anything. This is the place where actually pruning may take place. So if there are, so for an example, I updated this and I could see that, okay, because of this, I'm seeing alpha value is smaller and the update V I'm getting is much lesser than that. Then I will not be doing anything. Okay. I'll just update this value as V and will just go up. So these value or these things will never be considered for that case. Okay. We will not be trying it. These would be pruned in this, in that case. Okay. If this is not the case, that means if V was actually falling in between the range of alpha and beta, then what? Then we simply update the beta. Always remember, we always update beta in the mean node. Okay. So what would be that? It would be minimum of the older beta and the new value we have got of V. This is how we calculate. So it gets updated, then we try with this, then we try with this. That is how we keep on updating beta. And at any point, if I find while updating that my V value which I'm getting is less than alpha, I'll do not try other things. I'll just simply move on to the parent. Okay, I'll simply go to the parent, which you'll see in this current problem how beautifully in a smaller problem we are using it. The answer is very fast. Anybody can find it out. But just to see how do we complete the alpha beta searching, I'm just telling you this. Okay. Similar in case of max node, what we do is V is equal to max of the V value, which is by default the already value there, and the child value. So this is something which we keep on running for every child. But there is a point. If we run into this case, we simply return. We do not try for other child in that case. Okay. So this is the case. And over here, we look at this. At this place, I would be trying to update my alpha. But before that, if my beta, so see, if my my V value is actually greater than beta, then it's a problem. I'm already having a problem because I would be updating alpha in that case, and the problem would always be if I get alpha greater than equal to beta, because by default how we come up is alpha is in this side, beta in this side. We come from minus infinity while updating alpha. We come from positive infinity while coming to the left. So that's how we keep on updating. But if we ran into a moment where alpha is greater than equal to beta, then it's a problem. So just to avoid it, we do this check. Okay, this is where the pruning takes place. And the same thing over here. So if V is greater than equal to beta over here, we'll simply return V. We will not be doing anything. Okay. But if it is not the case, then I'll update my alpha as max of whatever the previous alpha and the right now V value. This is what is all about my alpha beta pruning, alpha beta search. Okay. And this is also, there would be pruning taking place if we have other child nodes which are left to identify, but at this point I found that V was coming out to be greater than beta. Nothing would be taking place. I would simply go up. Okay. But if all the childs are done and then I'm getting such kind of a case, then no pruning, but no update of alpha beta as well. Okay. I hope this makes sense. If you have any doubt, you can just comment down. You can just, ask your doubts into the Telegram group as well. So that was all about the algorithm. Let me just erase it all and then solve it up now for this problem. So we have this, 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 we have this. What are the values? 83172. 564, 5, 6 and 4. Okay. So if I talk about, so now see, the algorithm somehow, but now you'll learn some more steps. Okay. How does it proceed? So with respect to that, let's just write it down. So by default, as I mentioned, the alpha beta values are minus infinity and positive infinity. And this is a max node. So for this one, the value would be minus infinity, the V value. Okay. So always remember alpha, beta and V value. These are the nodes. These are the values associated with each node. So as we come down the child, we always copy the alpha and beta values. As we go up, we try to update alpha and beta value. So this is the case, and the by default, oh, sorry, this, there is a mistake. So this was This was basically a min node, and for a min node, yeah, it has to be infinity. It has to be minus infinity. Okay, let me just write down the by default values for all. Infinity, 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 infinity. Okay, on right side of the node, I'm writing the v value, and left side, I'm writing the alpha beta value. Minus alpha, sorry, minus infinity and infinity. Now what would be happening? You know all the values right now over at this place. So what would be the update? So you'll see this 8 is less than infinity. You'll modify this. Now you would like to change the beta, but before that you would check whether 8 is less than alpha or not. It's not, so you'll just modify this to 8. Okay, now the same thing, 3 and 8, which is minimum 3, so this gets updated to 3. Now the same thing, this also gets updated to 3. So the alpha beta values are updated to minus infinity and 3, and v value is also 3. Now if I talk about this, so I'll not be considering this thing over here. Okay, I'll not be taking these alpha beta upward. No, it would be these v value which will be helping me determine the alpha beta values of upper node or the parent nodes. So over here, this is 3. What would be happening with this? This is 3, this is minus infinity. So which one is max? 3 is max, so this gets updated to 3. Now just look at this. Is 3 less than your beta? The answer is yes, so this gets updated. It becomes 3 over here. A simple thing. Okay, so now we have 3 and infinity as these values, and this is 3, the value of node. Okay, now we come down this. So this is by default the value of the node. As we go down, we copy the value of alpha and beta. Okay, now this is 1. What do we get? We update this to 1. Now look at this. If I compare, alpha is actually greater than this v value. Can you try to recall? I want to update this beta over here, or let's suppose if I modify, you'll find alpha would be greater than beta. So it's a problem. Okay, so I will no longer be doing anything over here. That means this is pruned. I will not even be trying. I'll simply go above from here. Okay, we will simply go from here to the above node. What do we have? This is the 1. So there is no update on this particular value over here. So 3 is already better than 1. So no updates over here. Now we go a little further. So this gets updated to what? We get it updated to 3 at this point, and this gets updated to 3. I hope the idea is clear. What is happening? So because the minimum was 3, so we assigned it, and because you can see that the 3 is greater than alpha, so we have modified beta to 3 by calculating minimum of beta, existing beta, which is infinity comma 3. Hence we got 3 over here. Okay, I hope you remember that kind of a thing, that beta would be minimum of existing value plus the v value we have got, and alpha would be max of, in a same way, alpha comma v every time. Okay, and before that we check for this case, that for max node, I'm just writing it out. For a max node, I'm always checking that the v value should be less than equal to beta, or basically, yeah, it should be like this. For a min node, I would always be checking that v should be greater than equal to alpha. If this is not satisfied, in that case, what we do is we prune, or simply we do not do any update to alpha or beta. We go to the parent node directly. So this is clear. This is being pruned. We have the answer. I guess this was the D node, but still, just for the completion, I'm going to solve it further. So 3 minus infinity and 3. So this is copied over here, minus infinity and 3. This is copied over here, minus infinity and 3. Now what will happen? This is 2. This is infinity. This gets updated. See, this is 2. This is 3. Minimum of 3 comma 2, and 2 is already greater than your alpha. So it's fine. Minimum of 2 and 3. This is going to be 2 over here. Simple. Now what about this? No update. So hence no update. Okay, now I'll go up. This is the max node. 2 and minus infinity. This gets updated to 2 over here. I hope the idea is clear. I hope we are clear at this particular point. Now you can see I would try to modify the alpha value over here. Okay, so can I see over here? It's 2. It is less than your beta. Fine. It is going to be updated from max of existing value of alpha and v. So it's going to be 2 comma 3. Now the same value gets copied over here, 2 and 3. This is infinity. What would it be giving you? It gives you 6. Okay, what would so this will not be making any change over here. I hope you know that. Okay, so yeah, at this particular point there is no change. Now for the other child, what I'll be doing once again, so I'll look at this 4. What about the thing over here? If this is the 4, minimum of 6 and 4, what would be happening over here? So this gets 4 over here. What about any update over here? Would we be updating anything over here? The answer is simply no update with respect to this 2 and 3. I hope that particular idea is clear. So can you see, was there any pruning taking place over here? Did we saw that? The answer is, if I just check it out, we updated this to 6, and this is a min node. 6 was already greater than alpha. 6 was already greater than alpha, so we don't have any issue. Okay, I'll try to update my beta in that case. If 6 would have been less than alpha, then I need to go back and I would prune it, but no problem over here. So with 6, I tried checking out that, okay, 6 was greater than 2, it's fine. Now I'll try to modify beta. So minimum of 3 and 6 is 3, so no update in beta. So the node value was 6. The same goes for over here. So the same thing, it gets modified to 4, but no update over here. It is still fine. Okay, so 4 is, you can see, still greater than 2, and the minimum of 3 and 4 is 3 only, so no update over here with respect to this. Now as I come over here, what would be the thing which will be taking place? See, this is 4, this is a max node, so this gets modified 2 and 4, max of 2 and 4, this gets updated to 4. Now what about this on the same side? Now this is 4, I have updated it. At this particular point, I would try to update my alpha. Before updating alpha, I'll look at this, that whether it is less than beta or not. So the answer is, it is not less than beta, instead it is greater than beta. So I'll not be doing any change in alpha and beta. I'll simply go back from here. And this is going to be 4 value. Now, what about this? Minimum node, minimum of 3 and 4 is 3. So it's done. This is how alpha beta search was done at this particular point. And you can see only one place was there where we had a pruning, which was this 7, which was marked A, B, C, D, E, F, G, H. So this was the node which was actually pruned. Okay, I hope the idea is clear. A detailed explanation on alpha beta search. If you need any clarification, you can just comment down, or you can just ask me on the Telegram group as well. So let's move on to the next question. Again, a very good, amazing question based on A-star search. Amazing question. So what is being mentioned is, over here, we don't have an idea that, okay, what are the cost of moving from S to A, S to B, A to C, B to C, C to D, D to G, C to G. We don't have that idea. But what we know is, we have the heuristic function values. We know heuristic function values at each node, which is given over here in the diagram. You can see that. It's an amazing question. Amazing. Okay, this is a good question. You have the H values. Apart from that, the priority queue is given to you. The priority queue is already given to you, that, okay, in the first time, the priority queue would be having this only with F value. I hope you know, in A-star search, we calculate F as G plus H. This is the cost function up to that node from starting to the current node. What is the cost of my traversal or traveling up to that node? And H is heuristic function value, which tells me or give me the estimate of cost from this node to the goal node. This is how we calculate. So the value of F is also given at each step, you can see over here. So this is kind of the priority queue given at each subsequent step. Priority queue is given. Okay, and then the state value, the state which is there, and the F value for those, we already have it. Now what we need to find? We need to find what is the optimal cost from start to goal. Now how can I find if I don't know about the cost of transition? If I don't know, I won't be able to find it out. So how to do that, and what is the optimal path? We'll look at this, and this is a really good question. Okay, this is a simple one if you have the clarity around how do we solve it. So let's see this. So let me just write this down, what exactly are given to us. So we have H of A, sorry, what are these? H of S, H of S, H of A, H of B, H of C. All these values are given to us. H of we have Okay, up to D only we have, and h of g. This is 0. H of D is also 0. H of C is 2. H of B is 3. H of A is 5. H of S is 1. This is what we have. Okay. So, and we know the queue also. Let me just write down the priority queue as well. So we have it in like 1, 2, 3, 4, 5, 6. Yeah, 6 steps. So one is S and F is equal to 1 value. The other is B and F is equal to. So see, this is in the order. First value is this, B, and then is A, because you can see F value is lesser over here, and we keep the lower value in, like, this is the priority queue. So we always have the minimum value in the top, or the, like, in the front. So B, F is equal to 5, and then I'm having A and F is equal to 6. A, F is equal to 6, and then I'm having, sorry, C, F is equal to 7. F is equal to 7. C, F is equal to 6. Amazing. F is equal to 6. Then the next is D. So this D. F is equal to, what is the value? 5. G and F value is equal to 7. And then last we have G and F value is equal to 6. So now this is everything what we need over here. Okay. Now if I talk about this, we'll looking at this problem again and again, basically the diagram again and again. So I hope by now it is clear that first time I'll be having is this, the start node in the priority queue. So this would be expanded. And if I just talk about that, we already have the F value. And we know every time that F is equal to G plus H. Now that is a different thing, that for G, what is the path being taken? Always remember, G would always be telling you path, along the path you have taken, what is the cost for that. Okay. So if I talk about the first one, you'll be able to get the G value for that. So if I just write F of S is equal to G of S plus H of S, what do you get? F of S is already given to be 1. G of S you don't know, plus H of S is 1. So can you see that G of S is coming out to be 0? That's how you'll be getting all the values of G's, or basically the transition functions. Basically you'll be getting the values for these transitions over here. These values, what is the value over here, what is the value over here, you'll be getting these. Okay, and then you'll be able to find it out. So I hope by this it is clear that how would we be calculating this. So we have the value of G of S, and by default I know if I'm talking about GS, it is the starting point, so there is no path associated, so I would not be writing anything with respect to that. So let me just erase this now. We have gotten the idea that how we would be solving this problem. Now let's just proceed with this. How do we get the final answer? Okay. So let's just write once again what we have. Now for this, see, next time I have is B over here. So I'll try to find it out for B. What would it be? So F of B would be G of, see, when I'm talking about G of B, see, B was first on the priority queue. And how I'm reaching B? I'm reaching it from S. So let me just write G of SB, so that you know that I'm talking about cost at B from the path S to B, plus H of B. What is the value? This is 5. What is G of SB? We don't know. We need to find it out. Let's say X. What is H of B? We know it is 3. So we know this is going to be, this value is going to be 2. Okay. G of SB is going to be 2. This is what we have got by now. Okay. What about the A? So in a similar fashion, if I talk about this one, F of A would be equal to G of S to A is the total, like, cost you are having the transition, plus H of A. What do you get? This is 6. What is this? This is we don't know. Let's say X, plus what is this? H of A. We know it is 5. So x I got to know as 1. So g of SA is 1. So I'll just write it up for you. What are these values? So this is 1 I have gotten by now, and this is 2 I have gotten by now. Oh, this is 2 I have gotten by now. Okay. So I hope this idea is pretty much clear up to this point, what we have got for both of these, 1 and 2. Yeah. So let's move on to the next step. So again, I'll be repeating the same kind of a situation. So let me just erase this. And we have gotten some values. Okay. Now let's talk about the third step of priority queue. If I talk about that, what would be happening over here? So in this one, you can see that this cost is same. So I will not be checking anything out over here right now, because see, in the priority queue, we have, like we dequeue the node. For an example, this was the first time there in the queue. We dequeued it and then expanded its neighbor B and A in the order where the frontier, like the F value was in the sorted order. In a similar manner, when I dequeued B, I had its neighbor, what? C. So we have expanded C over here, and A value was already this. So this is already there. B has been dequeued. Now we got C because of B when we expanded B. Okay. So no change of this. We know the values. Let me just find out this. But while finding it out, remember this C is we are getting through B. This C we are getting through B. Remember that. So what I'll be getting? F of C will be equal to G of C. How am I getting to C at this point? How am I getting to C this at this point? SBC is the path I'm taking. SBC. SBC plus H of C. What is the function value at this point? If I talk about, so this is 7. If I talk about G of SBC, so see, in that case, I need to consider the path cost of S to B and B to C. B to C I don't know, but I have the idea about 2. S to B. So I'm talking about path cost from S to B to C. So SB is known, B to C is not known. So I'll just write it as 2 plus G of BC plus what is the cost? This one is 2. So what do you get as G of BC? You can see G of BC is coming out to be 2 plus 2, 4, 7 minus 4, 3. So we have gotten over here 3 value. Okay. Now the next step. So this is again done because A was same. There was no change in F value. C was just because of expansion of B. So up to this point we are done. Okay. Now C over here. We again got C. How is it possible? How is it possible? We again got C. So this is because now we tried A. We tried through A. A was there in the queue. It still needs to be calculated what is happening there. So because of A, I'm getting this now. Okay. And what I'll be getting, and C is already there. So there will not be, like a new C coming up. It would just be update on the same C node. So when I'm expanding this, it is going to get to C and see if I can have a new update which is costing me less. So over here you can see earlier it was costing 7, now it is costing 6. So it would be an update. So now it would be like this: F of C at that same point only, but right now it is SAC plus H of C. This is what we are getting to know at this particular point. What would be 6 is equal to G of SA was 1, I guess, plus G of AC, which we don't know, plus H of C was 2. So what do we get? G of AC is equal to 1 plus 2, 3, 6 minus, this is 3. So both are 3. So this is also 3 over here. Okay. I hope by now you have gotten it, that how my optimal path from S to C is of, what should I say? If I talk about S to C, if I talk about at C point, how my total estimated cost is coming out to be 6. You can see over here 1 plus 3, 4 over here. which is to reach at this point 4 plus 2 estimated cost from this to the final node. 4 plus 2 6. How I'm getting this? Okay, it's a simple update. We have gotten this, understood. So g of AC is also updated. So let me just remove these now. Again, we'll do the same thing. Now see, there is only C, which is updated C in the priority queue. So we will expand the neighbors of C corresponding to that. So we got D and G, and we got the F values for both. So accordingly, I'll just find it out for D and G. What exactly are these values? So let's just find out that. So if I talk about this, so what is this? F of D plus C. When I'm talking about both of these, this is how am I able to reach? Because of C. So how would I be writing it? Because of C. So I'll just write it up like this only, is equal to, so see, if I'm talking about this, what is the optimal path till this point? It was S, A, and then we reached C, and then I'm talking about D plus H of D. What is it? So if I talk about this one, what exactly I'm getting? This is 5. This I already know. SAC is known to me. This is 4. 4 plus G of C to D is not known. Let's say X plus H of D is 0. So what do I get over here? X is equal to 1. Okay, so that means this transition is giving me 1 over here. This value is 1. This particular thing. Okay. Now, in a similar manner, if I try calculating for G, what I'll be getting, let me just write F of G is equal to G of SAC, because that is the optimal path until C point, and then I'm directly reaching G plus H of G. What is this? This is already given to be 7 over here. What was the optimal path cost till C point? It was 4 plus X plus H of G. What is that? 0. So you can see X is coming out to be 3 over here. So that means, what is this path cost? This is corresponding to CG path. So let me just update. This is 3 now. Now we just need to get this, and we know what would be the final answer. So the optimal path I'm taking is this, because of this only, because of D only, when I expanded it, I am updating G. And you can see earlier it was 7, now I'm getting 6. So definitely because of D, I'm getting some advantage. That's why my optimal cost path is decreasing over here. Okay. So now because of D, I'll just find out what is this, and then hence I'll be getting the final answer, which is clear to me. It's 6. I hope you know the final answer. Okay. This was like a 1 mark question. If you just check it out, if somebody do a simple reasoning, they'll be having a final answer directly, that it's going to be 6, because I'm having F value 6 at this point. Okay, definitely it was 6 is the answer. But what would be this value? So by now, I guess I need not write the same thing. You know what would be the changes. At this point, the F value is 6, H is 0. It is just this part which is missing. So 1 plus 3, 4 plus 1, 5. What do you add to make it 6? 1. So this is the path over here. And the optimal cost path is this only. This one. Okay. So answer is 6, which was direct. If you know, if you just could have tried it, understood it well already, if you have the idea about A-star algorithm already. And if I talk about any edges, what are the cost of transitions, then it was a lengthy problem, a little lengthy, but this was the overall solution. I hope you have got this, you have enjoyed this problem. Thank you for watching out this video. Now next I'll be dropping the video for the mathematical portion. So in probability I have like more questions, so it would be taking a little time, but yeah, all of those would be dropped. And don't forget about the giveaway thing. So do register, share it with your friends, join the Telegram group, or our this thing as well, the what I'm falling short of word, the WhatsApp channel and the Telegram group.